Hey everyone, a quick question. Have you ever typed something into the search bar and thought, why am I seeing nothing useful? Search should help us find what we need, but sometimes it feels broken. Today, we'll see how search evolved from matching exact keywords to understanding what to actually mean. So, we've all been there. You type a specific intent based query. So by intent, I mean you will type something that you doesn't know the exact keyword, but then you will expect the search engine to understand the meaning. Like best card for airport lounge access into the search bar. And the system sometimes it's you with no search results found. It feels broken, right? That's because most of the search engines are still stuck in the 90s. Today, I'm gonna show you how we move from broken things to actual human intent. So this is the phase one. This is something I call it as a literal error. So system did not understand the meaning. They counted the words. Under the hood, most traditional search engines use something called as the BM25. So it's kind of an sophisticated word counting formula. So the algorithm looks at two main things. How many times a word appears in a document and how rare the word is across all the document. If a rare word appears many times in a document, BM25 says that this must be important. So if I search something very specific like Chase card benefits, BM25 is amazing. It finds the exact match instantly. But here's the problem. It has a zero understanding of the context. If I search best cards for international travel and the card description says no foreign transaction fees for overseas purchases, there are no shared words like international or overseas. So to the BM25, those are completely unrelated. So in this literal era, if the exact keyword is not there in the metadata or in the description, the result literally does not exist to the machine. So this is a simple idea. If I go and ask to assume this guy is a BM25, and if I go and ask, are there any travel guides related to Brazil? He might return me something which like the keyword matches to Brazil, but he might in the process skip the Amazon forest and the Rio de Janeiro and South American adventures, something like that. So this is like a pretty simple example of how the literal matching works. So next comes the vectors, and this is where the search fundamentally changed. We stopped asking, do the words match? And started asking, does the meaning match? Instead of treating text or words like a disconnected tokens, we pass the entire sentence through a neural network. So we usually call it as a transformer model. Okay. So, and the model converts the sentence into a long list of numbers. Not just three numbers, not just 10 numbers. So, but 384, sometimes 768, sometimes over 1,000 of dimensions based on the type of transformer model that you're going to use. Think of it like assigning a coordinate to every sentence in a mathematical universe. Now, instead of travel records being just two words, it becomes something like this. Assume this is how the travel words is being plotted into the three-dimensional, I mean, the multi-dimensional space. I cannot, by diagram, I can show you the multi-dimensional space, but imagine this with the two dimensions and see how these words are plotted in the graph. So these all have a similar meaning, and that's why they are in the similar neighborhood. So in this high dimensional space, similar ideas naturally cluster together. The travel rewards, the flight points, the airline miles, even though they share exact zero keywords, they land right next to each other because the model has learned that they often appear in similar context across millions of training example. Imagine meaning called as geography. All sports live in one continent, right? And all financial terms live in another. And all travel related phrases live in their own neighborhood. BM25 only checks if the street names match. But vector search checks if all the houses are there in the same neighborhood. Okay, so let us check how the distance calculation actually works. So we don't need a math, okay? Search becomes a distance problem. Instead of counting words, we measure how far two vectors are from each other. So the closer the distances, the higher the similarities. The farther the distances, the less relevant it is. So we use some techniques, and one is called as a cosine similarity. It is the distance we use to find for two vectors in the high dimensional space. So yeah, search stopped matching strings. It started matching concepts. Of course, vectors are not magic. They approximate meaning. Truly don't understand. But they are better than, like the blind word counting, right? Okay, let's go to the next concept. But there's a catch. Vector search can be too smart. If I specifically ask for a Chase, Sapphire preferred, I don't want MX equivalent or delta equivalent, even if they are semantically similar. Sometimes literal accuracy is the only thing that matters. This is very, very well problem that every AI engineer hits. So we have seen the two extremes, right? What are the potential advantages and disadvantages of keyword matching, and what are the pros and cons of vector matching? On one hand, keyword search is incredibly precise, but it is rigid, right? It only gives what you specifically ask for. On the other hand, vector is brilliant at understanding the vibe and the context, but it can sometimes be too broad. This is the core dilemma of the modern search. So, what if we don't have to choose? What if we could combine the literal power of a keyword searching with the intuitive mind of the librarian? As a summary, use BM25 or the keyword approach when you need a precision, like a specific product IDs or specific numbers or even unique names. When you are searching for broader themes or complex natural language questions, use a vector search. So comes the hybrid search. So it's a type of approach that combines the keyword based methods and the vector based methods. So each has its own strengths, right? What we have taken a look at the previous slides. So here comes the tricky part. Their scores are really not compatible. You can't just add the scores together because BM25 scores varies, which is greater than 10, whereas the vector scores lies between 0 and 1. Why? Because it's the distance between two vectors, right? So we usually find the distance between two vectors using a formula called as a cosine similarity. So we all know that the value lies between 0 and 1. If you're gonna add it, obviously BM25 is going to bully, right? So yeah, it's like the apple versus orange problem. A BM25 score of 18 and a vector of 0.8 live in a different universe. Remember this, scores are a lie, ranks are the truth. So instead of trusting raw scores, which are not even comparable between BM25 and vector search, RRF focused only on rank position. It is also this type of method is called as a reciprocal rank fusion. So it doesn't ask like what score did this document get. Instead, it asks where did this document rank in each system. Each retriever, the keyword and the vector, gives its own ranked list. If a document appears high in both the list, it gets rewarded. So top 3 in keyword and top 4 in vector is a very strong signal. But rank 2 in one but missing in other is probably weaker. And rank 20 in both gets the low importance. So RRF combines these rankings using a simple formula that gives more weight to the higher positions. So why this works? Because prevents BM25's large numeric scores by overpowering the vector scores. Think of this like a democratic voting system. So each search engine casts vote based on the ranking. If both agree something is important, it rises to the top. No single search engine can dominate the final decision. Now let's talk about the architectural trap. When teams decide to go hybrid, their first instinct is to usually grab what they know. They use Solr or OpenSearch for the keyword database, and then like a Pinecone or Milvus or any other thing for a vector database. So they need two database for two different searches to happen, right? On paperwork, it just works fine, but in production, it's a trap. You are managing two different sources of truth. If a product price changes in your keyword store, but the vector embedding hasn't updated yet, your searching results becomes an hallucination. You're dealing with the double API overload, double latency, and frankly, double the chance of something breaking at 3 a.m. You don't need a bigger tool bit, you need a smarter tool. That's why Elasticsearch wins the hybrid game. When people build hybrid search themselves, they often end up with what I call as a Frankenstein architecture. Google it and check what it actually means. So one system for keyword and another system for vector search. Custom code to merge result. It works, but it's stitched together. And stitched system always introduce delays, synchronization delays, and ranking inconsistencies, operational complexity, two failure modes and scaling paths. That's not a right strategy, right? That's a technical depth that is waiting to grow. So we don't want a two brains. In most of the hybrid setup, keyword lives in one database and vector lives in another. So if an update comes, it just goes in chaos. So there comes the unified brain architecture. This is where Elasticsearch changes the game. In Elasticsearch, text fields is there, dense vector embeddings, and then metadata and filters are present. So all these live inside the same document, in the same index, on the same shard. So one product is one unified entity. So by embeddings, what I mean is the way you convert a word into a vector. And metadata is the description of what actually the record talks about. So when one thing updates, it updates everything together. There is no cross-system communication, no replication gap, and no eventual consistency problem because there is nothing to sync. Hybrid is not actually happening in your application code. It's actually happening inside the engine where BM25 executes and where the RRF ranking fuses, all within the same distributed execution ecosystem. So you're not calling two databases and merging it in a Python or whatever language of your comfort. You're running two retrieval strategies inside one distributed brain. That's called as an architectural coherence, right? So at the end of the day, your hybrid search shouldn't live in two databases arguing with each other. It should live in one brain making one decision. That's why Elasticsearch comes into picture, which saves all these problems. Okay. So how do we actually talk to a vector database? So we use a process called as embedding. If you type like flight from US to China, first the system performs tokenization. It's not just looking at words, it's looking at prefixes, suffixes, and context. Then it passes those tokens through a transformer model. So transformer model converts the words into vectors. This is the actual heavy lifter. It doesn't just see the flight, it sees the relationship between US and China and the concept of travel. Finally, it splits out a 384 dimensional vector. To us, it's just a messy list of numbers. But to Elasticsearch, it's a specific GPS coordinate in the geography of meaning. No matter how long or short your query is, the output is always a fixed length vector ready for high speed distance calculation. So now here's a secret for getting better search results. Machines actually prefer sentences over spreadsheets. So if you just feed a vector model a raw JSON object like annual fee 9 to 5, the model sees the numbers and keys, but it loses the soul of the data. To fix this, we perform a narrative transformation. We take those raw attributes and bake them into a descriptive sentence like the chase sapphire preferred features, a 95 annual degree, and offers a 3x on the travel expenses. So why do we do this? Because the transformer model we use for embeddings were trained on books, Wikipedia, and articles. They are literally by nature. But turning your data into a story, you are speaking the model's native language, which leads to much more accurate neighborhood places in your vector space. Um, in the lab, most similar results is the winner. In the real world, most valuable results is the winner. This is where the business layer comes in. Once we have the RRF score, the perfect blend of keyword and the vector, we apply a business boost. We use this formula to nudge certain results on the top. Maybe you want to filter out the credit cards the user already owns. Maybe you want to give a slight 10% on the cards to no annual fees because that's what converts best. That what converts best right now, right? So without this layer, you are just doing a math project. With it, you are running a business because at the end of the day, relevance without business logic is just a math. So we have covered a lot of ground today, but if you can take away three things, let it be. First, keyword search is not dead. It's your anchor for precision. And then vector search is your power for understanding the why behind every query. Hybrid search is the only way to deliver a production grade experience, or I cannot say that it has the only way. It is one of the effective ways to deliver a production grade experience that doesn't frustrate the users. We saw that you just can't add scores together. You need a system like RRF to let two engines vote on what matters. Because if there is one thing I want you to remember from this deep dive into AI search is that scores are a lie and ranks are the truth. The era of just hoping the user types the right keyword is over. We moved past the limitations of string and entered to the world of meaning. Search is no longer about matching characters on the screen. It's about matching the human intention behind them. The tools are here, the architecture is ready, and the results speak for themselves. So I have one question left for you. Are you ready to vectorize your thinking? Thanks to everyone for watching. For a deep dive into the actual implementation, check out the blog in the description. That wraps our session. If you want to see the full technical implementation, step-by-step code example, and detailed explanation, the blog has all the bits. And also I have attached the GitHub link for you to explore further. Thank you, everyone. Thank you. And please do say your point of view in the description. And is there any other thing that I can cover in my next video? Do let me know. Thank you, everyone, for watching.